Today I'm going to teach you about integration by partial fractions. To follow along with these notes, go to my website and print out the notes and you can fill them in along with me. Partial fractions is an integration method for integrals of rational functions, like this one, where we have a polynomial on the top and a polynomial on the bottom. And to do this, we need some method to break up a big fraction like this into a sum of simpler fractions. Some number divided by a denominator plus another number divided by another denominator. This is probably something you haven't done before, although you have gone in the other direction many times. For example, 1/2 plus 2/3. You have to find a common denominator. So for 2 and 3 that would be 6. So you say 1/2 is 3/6, 2/3 is 4/6, and so you add the tops and you get 7/6. So now we're going backwards. We're saying, how do you start with 7/6 and know to decompose that into 1/2 plus 2/3? And the first big observation is that the 2 and the 3 are factors of 6. So the same thing will hold in a case of a rational function like this one. The two denominators here are going to be factors of this big denominator here. So you have to kind of whip out and dust off your old factoring skills and say, this quadratic at the bottom factors as x minus 3 times x plus 1. So this denominator is going to be x minus 3, and that denominator is going to be x plus 1. So that's what the question marks are. They're just factors. The harder question is then, what exactly are the numbers a and b? And to do that, we have to do a little bit of work. So the first step is to clear the denominators out of the above equation. So we take this equation, 5x minus 3 over x minus 3 times x plus 1 equals a over x minus 3 plus b over x plus 1. And we clear out the denominators. So multiply both sides by this big denominator, x minus 3 times x plus 1, and multiply each of the terms by that. So let's multiply this term by x minus 3, x plus 1. Then let's multiply this term by x minus 3, x plus 1. And then what should happen is that things cancel out and all the denominators will clear away. And you get something simpler. So we now have 5x minus 3 equals a times x plus 1 plus b times x minus 3. Now, at this point, you have two choices of what to do with this expression. The more conventional way I'll show you first is to solve a system of equations. So let me show you how to do that. You take this equation and first expand it, distribute the a and the b. So we get 5x minus 3 equals ax plus a plus bx minus 3b. And then we're going to collect terms by whether they have an x in them or not. So it will look like 5x minus 3 equals a plus b x plus a minus 3b. So we've sorted the x terms and factored out a coefficient, and then we've put the rest of them here. Now, why would we do that? Well, the key is that this equation is not just true for some values of x, but it's true for all values of x. This is called an identity. It's identically true, and some people would indicate it by putting a third line for the equal sign. That means that this expression, a plus bx plus a minus 3b, always has to match 5x minus 3 exactly, meaning that the a plus b, the number in front of the x, must be 5. So we can write an equation that the a plus b must be 5. And the rest of it, the a minus 3b, must be the constant negative 3 at the end. So taking advantage of the fact that this is an identity yields these two equations. That's the only way this side could be exactly the same as this side for all values of x. Now you have to dust off your equation solving skills for systems of equations and remember how to solve this for a and b. So for example, we could subtract these two equations to get b minus negative 3b is 4b, and the a's cancel. And on the right-hand side, 5 minus negative 3 is 8. So we get b equals 2, which we can then plug back into the first one to get a plus 2 equals 5. So we can do that mentally, that a equals 3. And we've got it. b equals 2 and a equals 3 are the correct numbers for the original problem up here. So that should be a 3 and that should be a 2. Before we continue with that problem, I just want to show you an alternative method that I really, really like for how to do this faster, and some would say more efficiently. It's called the plug-in method, and it also takes advantage of the fact that this thing is identically true for all x. Since it's true for all x, it's true for, in particular, for example, if x equals negative 1, this must be true. Now, why did I choose x equals negative 1? Well, if you plug in x equals negative 1 into this, what does it say? It says 5 times negative 1 minus 3, that's negative 8, equals a times negative 1 plus 1, that's 0. So this term drops out. And you get b times negative 1 minus 3 is negative 4. So you get b times negative 4, or negative 4b. So you just get negative 8 equals negative 4b. So b equals 2. And look how quick it was to get b equals 2. We didn't have to distribute the a and the b, collect the like terms, or solve a system. Now, notice again I chose the negative 1 to make this x plus 1 0. So by the same logic, if I choose x equals 3, this b term will be 0. So I'm going to do that. Let x equals 3, and now this reads 5 times 3 minus 3, that's 12, equals a times 3 plus 1, that's 4, plus b times 0, and then this drops out. I get 12 equals negative 4a, so a equals 3. And notice we get the same numbers, a equals 3, b equals 2, no matter which method we use. I happen to like this method. I think it's neat and quick. But you should know this method too, because this does not always work in all cases. Now how do we finish the problem? Now that we know a equals 3 and b equals 2, go to the next page, and it says, then do the two simpler integrals that result. So now we know, here's what I mean, now we know that our original integral, which was this, can now be broken up. When this is broken up into two partial fractions, we get, it was a over x minus 3 plus b over x plus 1, and the a was 3 and the b was 2, and now these two integrals are easy, so we can just do them. This one, for example, the first expression, the antiderivative is 3 natural log x minus 3, and the other one is 2 natural log absolute value x plus 1. You throw on a plus c, and you're done. And that is partial fractions in a nutshell. So let's do another example from start to finish. Here we go. My suggestion for this problem is to, and most of these, is to do all your scratch work, your partial fractions on the right side, and then just do the integral on the left side. So let's do that. 1 over x squared minus 8x plus 15 is going to break up into a over something plus b over something else. And what are these two going to be? Well, the factors of x squared minus 8x plus 15 are x minus 5 and x minus 3. So we can just fill those in. as denominators. So our next step is to clear the denominators from this equation. So let's multiply this left side by the common denominator, which is x minus 5 times x minus 3. If we do that, so I'll squeeze that up here, x minus 3, sorry, that should be a minus sign. This cancels with that, and we just get 1 equals. If we multiply this term by x minus 5 times x minus 3, the x minus 5's cancel and we get a times x minus 3. If we do the same thing here, the x minus 3's will cancel and we can get b times x minus 5. So now we have this, and at this point recall that we have two choices. We can either distribute the a and the b, collect like terms by powers of x, and then solve a system, or we can do the plug-in method. So I will do the plug-in method just because it's faster here. Let's let x equal 3. That will make the a term 0, and this equation becomes 1 equals b times 3 minus 5, so negative 2b, giving us b is negative 1/2. If we say that in this identity x equals 5, then the b term will drop out, and we get 1 equals a times 2. So 1 is 2a, meaning a is 1/2. Now that we've done all of our scratch work over here, we know how this will decompose. So let's go back to the integral. Now that we know that this will decompose into a over x minus 5. Well, a is 1/2, so we get 1/2 over x minus 5. And then b over x minus 3. Well, b is negative 1/2, so I'll write minus 1/2 over x minus 3 dx. Now we can easily do this integral. That's 1/2 natural log x minus 5. This one is minus 1/2 natural log x minus 3. And then we throw on a plus c, circle it, and we are done. So hopefully from these two examples you're starting to get the hang of what this partial fractions method looks like. So let's kick it up a notch and do a couple of things that might be a little trickier with partial fractions, because some crazy things can happen. So look on this next page. Here's what can happen that's a little strange. What if there's a repeated linear factor when you factor the bottom? For example, this thing factors as x plus 2 times x plus 2, or x plus 2 squared. So it might be tempting to write this when you're decomposing this into partial fractions. A over b over, and the two factors are x plus 2 and x plus 2. So unfortunately, this choice of denominators doesn't work. The reason is that that the common denominator between x plus 2 and x plus 2 is just x plus 2, not x plus 2 squared. So how do we remedy that? Well, it turns out there's a quick way to remedy it. You leave the first one as x plus 2, but the second one you make into x plus 2 squared. And it's as simple as that. That setup will in fact work for this case. If there's a repeated linear factor, keep the first one as is and then square the second one. And then leave the top as just two numbers, a and b, and it will work. Here's another thing that could happen. What if you have an irreducible quadratic factor in the denominator? By which I mean an unfactorable quadratic like x squared plus 1. So let's see if we can set up this one as a decomposition into partial fractions. So let's write 4 over 2x divided by x squared plus 1 times x minus 1 squared. Well, let's start by setting up what we do know how to deal with, which is this x minus 1 squared. So we know from up here that if there's a repeated linear factor, like x minus 1 and x minus 1, we should keep one of the x minus 1's, and then make the second x minus 1 squared. So 1 not squared and 1 squared. The question is, how do we deal with this irreducible quadratic factor x squared plus 1? Well, there's nothing you can do with it. It has no factors except for itself, x squared plus 1. So what do you do at the top? It turns out that on the top, in this case, you can't just put a number like a, b, c, or d. You have to put cx plus d. That's because the most generic thing with lower degree than this denominator, lower degree than x squared, is a linear expression like cx to the 1 plus d. So a, b, c, and d are numbers, but above the irreducible quadratic, you have to put the linear expression cx plus d, and then proceed as we did before. Notice that in the case of a quadratic like this, x plus 2 squared in the denominator, you don't do that. You can just put a number. But if it's irreducible, unfactorable, like x squared plus 1, you have to put cx plus d on the top. The other thing that can happen is, what if the degree of the denominator is not larger than the degree of the numerator? So here you have an x cubed in the numerator, but only an x squared in the denominator. All these techniques only work if the degree of the numerator is less. So what you first have to do is everyone's favorite long division of polynomials. Like this, x squared minus 2x minus 3 divides into 2x cubed minus 4x squared minus x minus 3. And you have to do this whole process. And after you do that, you'll get something like 2x plus some remainder, like this. I think this is how this one comes out. And so now you've broken this fraction up into a 2x, which is easy to integrate, plus this thing, which you now know how to integrate. In fact, this one is exactly the first example from the first page that we did earlier. So what you do is do long division, and then do partial fractions on the resulting remainder. Okay, let's go to the next page, and we will do another example. This will be our last example with partial fractions. I printed a time-saving tip that sometimes you can't use the plug-in method all alone. You can use it to find as many constants as you can, but you might have to solve a smaller system to find the rest of the constants. So let's do that. In this case, let's put all our scratch work on the right-hand side here. Let's do this. X squared plus 2x minus 1 over x to the 4th minus x squared. How does that factor? Well, if we pull out an x squared, we are left with x squared minus 1, which also factors as x plus 1 times x minus 1. Sorry, that says x minus 1. And how should this break up? Well, the x plus 1 and the x minus 1, we know how to deal with that. X plus 1, x minus 1, with a and b on the top. How do we deal with the x squared? Well, that is a repeated linear factor. It's like an x times another x. So recall that we put an x here, and then instead of another x, we square it. So it looks like a, b, c, and d on the top, and x plus 1, x minus 1, x, and x squared on the bottom. Let's clear the fractions from this. Let's multiply everything, each of these 5 terms, this, by the whole denominator here. Then we would be left with, on the left side, just x squared plus 2x minus 1. For this a term, the x plus 1 cancels, and we're left with a x squared x minus 1. Similar things happen to the other terms, so I will just write them out. b times x squared times x plus 1, c times x, x plus 1, x minus 1, and then d, x plus 1, x minus 1. That says d times x plus 1 times x minus 1 is what I tried to squeeze in there, right there. So if you were going to just solve a system with this, distribute the a, b, c, and d and get 4 equations with 4 unknowns, that might take a while. And I'm afraid that on an exam you might not have time to do that. So that's why I gave this tip. Use the plug-in method to find as many as you can. You might be left with 1 or 2 of them, and you might have a smaller system. So let's do it. If we let x equals 0, for example, the x squared becomes 0. So the a term, the b term, and the c term here, because of that x, drop out. And we're just left with the d term. So we get minus 1 on this side equals negative 1d, giving us immediately d equals 1. Similarly, if we let x equals 1, our equation gives us 2 equals 2b. So b equals 1. And if we let x equals negative 1, our equation gives us negative 2 equals negative 2a, so a equals 1. You can pause the video if you need to convince yourself that these are the equations and the results that you get from making these substitutions. Now, there's nothing else we can plug in that's useful. We already tried 0, 1, and negative 1. And those are the only numbers that will make these things here, these denominators, or these factors here, 0. So we still don't know the b. So how do we find out the b? Well, let's just see what our equation here now says. It says x squared plus 2x minus 1 equals, we know a, b, and d are now 1. So x squared times x minus 1 plus x squared times x plus 1 plus c x, x minus 1, x plus 1 plus x plus 1, x minus 1. Now, let's distribute all these x squareds, collect all the terms, and you can do that on your own if you want, but how it ends up being is the right-hand side equals c plus 2x cubed plus x squared minus cx minus 1. And still on the left-hand side you have this, x squared minus, or plus 2x minus 1. So the x squareds check out, this x squared and this x squared match. The minus 1s check out, but there is no x cubed. Here there are 0 x cubes, and here there are c plus 2x cubes, yielding the equation 0 is c plus 2. And that tells us immediately what our c is. Our c is negative 2. You could also have seen that, by the way, from the negative cx has to match up with positive 2x. So in this case, our system that we had to solve was really only one equation, but it just goes to show you that this plug-in method doesn't always find all the constants. Sometimes you have to go back, plug in what you do know, and then figure out the rest with what you have. So, going back to here, we now know that this decomposes as a over x plus 1, b over x minus 1, c over x, and d over x squared. And they were all 1 except for c, which was negative 2. So let's do that. 1, 1, the c was negative 2, and the d was 1. And the denominators were like this. And now this is much easier. Don't forget the dx. This is much easier. You can now solve this on your own That's some kind of natural log, so is that, so is that. And that's, notice, not a natural log. This is just a power function like x to the negative 2. So be careful. Don't assume these are always natural logs. And you can just finish this on your own now that it's easy. Okay, let's talk about a couple more things here. One thing I'm telling you now, you can do more practice, so here's a few good ones. This one doesn't look like it's a partial fractions question because it has this radical in it. And we talked about radicals for using trig substitutions, but this is not a quadratic in x under the radical, so you can't do it that way. So a tip that sometimes works for integrals involving radicals is to make a u substitution where u is the whole radical. Like in this case, u equals square root x plus 1. Now why am I talking about that here? Well, if you make this substitution and you do the work, and I want you to do this on your own, you'll find that what happens is this then becomes a purely rational expression with u that has a polynomial on the top, a polynomial on the bottom, and no radicals anywhere to be seen. And you can use the partial fractions method to do that problem and then substitute back in for x. So you can do that on your own. Now, one last thing to mention with partial fractions. Go to the last page of notes here. It's called Weierstrass substitution. And this is for integrating rational functions of sine, cosine, and other trig functions. So things that look like the examples at the bottom of a page. Notice these are fractions, including this one. That's really 1 over sine x. But these are fractions not in x, but in sine x or cosine x. So there's this clever substitution that no one would ever really think of on their own. And here's how it works. First, write all trig functions in terms of sine and cosine. And you make this clever substitution, u equals tangent of x over 2. I don't know how the person who came up with this thought of it. Maybe it was Weierstrass, or maybe it's just named after him. But this clever choice changes sine, cosine, and dx in the integral as follows. The sine x, by trigonometric identities and some algebra, eventually becomes blah, 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 2u divided by 1 plus u squared. So just a rational function of u. The same thing happens to cosine x, and the same thing happens to dx. So you end up with this rational function with u's in it, which is why I'm talking about it in this partial fractions video. What you do is you use the partial fractions method to do the integral with u's in it, and then you change back from u to x, putting back in tangent of x over 2 for u. So here are some examples. You're free to do them on your own. I'm not going to do any of these outright for you. I will just start the fourth one for you. So if you make this substitution, for example, u equals tangent of x over 2, the sine x here becomes 2u over 1 plus u squared, according to all of this algebra we did up here. The dx becomes 2 du over 1 plus u squared. So this dx becomes 2 du over 1 plus u squared. And on the bottom, we get 1 plus sine x, which is this. And you can do a little algebra to simplify this, but it shouldn't be too hard to convince you that this comes out to be a rational function, and you can use partial fractions to decompose it, do the integral, and then change back from u to x. And that's all I have to say about partial fractions. You're now ready to do your assigned homework on this topic.